Good afternoon, everyone. Welcome to today's SANCOLD YPF webinar. We're pleased to have you join us for what promises to be an engaging and technically rich session. Our topic today is CFD analysis of spillway discharge coefficients for the Steenbras dams, a fascinating intersection of traditional hydraulic engineering and advanced modeling techniques. We are delighted to welcome our speaker, Pierre Kluter, who led this study. Pierre is a professional engineering technologist and a member of SAICI. He holds a Master of Engineering in Civil Engineering Water from Stellenbosch University, as well as a BSc Honours in Civil Engineering Water Resources from the University of Pretoria. Pierre has been with Zutari for the past 11 years, where he is currently based in the Pretoria office, working as a hydraulic designer and modeler. His experience spans hydraulic design and modeling, and he brings both practical and analytical insights to the challenges involved in spillway performance analysis. Before we hand over to Pierre, just a quick note on logistics. The session is being recorded and will be made available after the event. Your microphones and cameras have been disabled to prevent background noise, but you'll be able to drop your questions in the chat at any time, and we will address it during the Q&A session at the end of the presentation. You will also be able to raise your hand at the end of the presentation to ask your questions directly to Pierre, in which case I will unmute you and you will then be able to just discuss with him whatever your issues are. So without any further ado, welcome, Pierre. The floor is yours.
Thank you, Ashley, for the introduction and also the handover. Good afternoon, everyone. I know this is a Wednesday, so obviously everyone is super keen at staying awake. So I'll do my level best at keeping you entertained for the next hour or so. I'll just quickly now share my screen. Ashley, if you can just confirm that it's coming through.
Yes, everything's good.
Perfect. Okay, as Ashley just mentioned, what the study entailed was basically using computational fluid dynamic modeling to determine the impact of unique geometry encountered with the Steenbras lower and upper dam spillways. But we'll get to that in a second. I'm just going to quickly take this moment to obviously market who we are and what we do. So I work for Zutari, which is a multidisciplinary engineering consultancy, which is also internationally available. And we've also been around for a couple of years, as you can basically see from the timeline at the bottom. I work mainly in the water market, which has also got a couple of sub-disciplines located within it. But the majority of those that I kind of work in is bulk conveyance, as well as dams and hydro. So that gives me an excellent opportunity for being kind of open to a lot of interesting hydraulic aspects. So also to kind of quickly illustrate the interesting stuff that we do and we get exposed to at the water market for Zutari is obviously very unique situations which are maybe not that standard catalog type of designs. So, you know, having CFD capabilities available to undertake studies for all these interesting projects is obviously a key thing for us. Being in the dams and hydro space, obviously it's very imperative to be able to quantify the impact of your designs and the performance of your designs as well. So those are just a quick couple of visual examples of the type of projects that we do, so that I just don't bore you too much with that. Obviously with bulk pipelines also we typically look at pre-swirl conditions before you get to your pump on your suction side as well. So that's also a very good application of the software for us. Okay, so with that quick intro, we can drop into the main theme of today's webinar. So to quickly just give you an overview of Steenbras Dam, it's a dam located in the Western Cape, close to the Hottentots mountain range. which you can actually basically see in the northern part of the dam. It's located or it's broken up into two different dams, which is basically the upper Steenbras dam, which is located towards the east, and then the lower Steenbras dam, which is located to the west. Now, both these dams obviously do have spillways of their own. The upper dam spillway you can see in the lower right image, which is a nice WES standard USBR spillway. And then the lower dam spillway is the one that you can see in the image to the top left, which is somewhat of a OG spillway, but not in the traditional sense of it that you would be encountered in design documentation. So the main idea of the study obviously was to understand the discharge head relationship of these two spillways. This image also just kind of depicts a contour map of the layout, so you can see it. The dam is nice, located at the top of that mountain range, which is also pretty unique. So yeah, just a quick bit of background. The Steenbras Dam, as I mentioned, is two different interconnected reservoirs. The lower dam was originally completed in 1921. So it's been around for 100 plus years. It's got a wall height of approximately 28 meters, and then also a gross storage volume of about 36 million cubes. The upper dam was later constructed and completed in 1977. It consists of a main embankment dam, which is about 34 meters in height, as well as a saddle dam of approximately 13 meters in height. And it has a storage volume of 31 million cubic meters. And it also forms part of the pumped hydro storage scheme at the Steenbras dam. So the main objective of the study was to actually do a dam safety evaluation of the dam, both the upper and the lower, and then also to do an evaluation of the flood routing capabilities of the two dams. But for that, you would obviously require an accurate stage storage relationship for both spillways, and that would eventually feed into a 2D numerical model that was set up as well. But due to the unique shape of the lower dam spillway, the approved professional person prompted the use of CFD to determine the accurate head versus flow rate relationship. The upper dam spillway, as I mentioned, is a standard USBR WS spillway, from which the head flow relationship can actually be easily determined. But the APP still recommended the use of CFD just to verify the head discharge relationship, which I obviously didn't say no to. Okay, so tackling the first dam, the upper dam spillway, you can kind of see the spillway in plan to the right. It's got a nice 70-meter spillway length with a 10-meter low flow spillway section to the right. The top left image actually shows the profile of the spillway, as well as the section AA to the top right of the spillway as well. And then the bottom left image is just a very nice image for reference to see what the spillway looks like. Yes. Okay, so for any CFD analysis, we obviously do need a control volume. And because the upper dam spillway was very monotonous or singular section throughout the length of the spillway, we decided on using a unit width approach for the spillway capacity determination. So we took a 1 meter unit width and basically did what you can almost consider as being a two-dimensional CFD analysis. And then also because the low flow spillway and the remaining main spillway profile was exactly the same, just with a 50 millimeter offset, we could still just do one unit width section to determine the relationship for the flow rate versus the flow depth. and then obviously just multiply that by the entire length of the spillway, and then also just do a small adjustment for the 50 mil drop for the low flow spillway. Okay, so with any CFD work, again, you do need a control volume, as I mentioned, and then from that you would need to set your boundary conditions. So for the upper spillway, we had a pressure inlet to which we assigned an inflow depth. Pressure outlet to the top, which is basically just opening it to atmosphere, because we effectively do have two-phase or multi-phase flow, and then a pressure outlet to the right, from which water can actually exit the computational domain. And then the spillway itself is a wall boundary, which effectively just means that we can assign a boundary layer to it, and also compute and take into account the friction losses that you would typically experience. Then the left and right hand planes were selected to be symmetry planes, so that they basically almost act as a glass surface without any friction, so those would not influence the main spillway hydraulics in any shape or form. From there, we typically then generate a numerical mesh, and then also add mesh refinement throughout the domain at the places where we do want more detailed information or finer definition in results. In this case, it would be the water elevation or on the upstream end, so that we can accurately capture and record that. And then on the outflow boundary, we would just record the flow rates. Okay, for the upper Steenbras spillway, we had about 80,000 polyhedral cells, each of which could contain water, air, or a combination of both, hence the multi-phase flow modeling approach. And then the mesh size was between 25 to 250 millimeters in size, depending on obviously the areas of interest. As we were determining a stage discharge relationship, we obviously needed to run it for multiple upstream depths, and then obviously record the resulting flow rates. So for the upper dam, we did 9 runs, which we gradually ramped up the inlet depth, as you can see in the images from left to right, and then from bottom, top to bottom, and eventually ending up at what you see to the bottom right, where we've got full flow conditions. We also did assign a bit of a tailwater to mimic the effect of any downstream inundation or downstream backwater effects that you might encounter. And then eventually ending up at a unit width versus head relationship, as what can be seen on the left graph. As I mentioned, we then can just multiply that by the entire spillway length to get to a total discharge versus flow depth relationship. But because we did have the 10-meter low flow section with a 50 mil offset vertically, we did make an adjustment to that, which you can kind of see in the chart to the right. That 0.21 cubic meters per second is basically the maximum flow for the first 50 millimeters of the low flow spillway, and from there on, the main spillway starts to contribute to flow for over the spillway. Okay, now for the more interesting and fun one is the Steenbras lower dam. As I mentioned, this dam is almost similar to an OG, except that it's got a backward slanting upstream face, and the OG profile is actually cut short. So the top right-hand image shows the initial first lift of the Steenbras dam, which is indicated in blue, and then the second round of lifting of the dam is indicated in the red line. So there was not a lot of space, and having a fully fledged OG constructed would have been a fairly high cost implication. So they went for this type of option where they stop the OG profile basically. So for our purposes, we obviously wanted to obtain a very accurate head discharge relationship over this spillway. So you can kind of see the spillway where it's located along the dam wall in the right-hand image. And then the left-hand image also indicates the spillway as it is just starting to overflow. Okay, so for the lower dam spillway, we obviously received a very detailed survey, which was great to get that type of information. It's not always that readily available. And then apart from just the main survey of the greater area, we also got a fairly detailed survey of the crest of the dam wall, which is also very interesting to kind of see the deviation that crest had from just having a singular overflow elevation. It differed in about 40 or about by 40 mil from minimum point to maximum point, which is probably not that great, but still very interesting to note that you get those variations. So again, we did want to go for the unit width approach in determining the stage discharge relationship. But now the question would be what elevation to use if you look at this jagged profile for the crest. So we went for an approach where we did a weighted average to determine the average crest elevation. And from that, we basically identified a point on the crest where we can actually then have a control volume, which would represent that overflow elevation. So you can see the control volume to the right. And then again, similar to the upper dam spillway, we assign different boundaries to the different areas in the solution space. Again, having a pressure inlet to provide a fixed upstream elevation, provide a pressure outlet, and in this case it was almost just a free flow or free fall conditions, but just also ensuring that the rear of the nap is still ventilated. So one of these upstream faces, we also provided a pressure outlet and assigned atmospheric pressure or atmospheric conditions to it. And then again, the upper boundaries, we assigned just atmospheric pressure to it, and then finally assigning a wall boundary to whatever you can actually see in gray over there, and then again having two symmetry planes to both sides of the control volume. The mesh for this control volume was a bit more than the upper dam spillway. We looked at about 300,000 polyhedral elements, so really good detail. Again, which can contain either fluid or air or a combination. And then the mesh size ranged from 5 millimeters up to 250 millimeters. So the 5 millimeter cells were actually placed on that upstream face or the OG crest of the spillway, so that we could just determine if there was any separation of flow from that crest during high flow conditions, which was not present. But using a small enough cell size, we could actually at least try and see that result. Okay, for the lower dam, we did a couple of more runs, which totaled about 12. Again, gradually ramping up the inlet level, and then recording the outflow flow rates for each of those levels, and then eventually ending up at the image that you see to the bottom right. That is basically at NOC of the dam, just to highlight that for a future slide. Okay. So typically with CFD models, if you don't run it on the cluster, but you just do local computing, you would typically have a lot of waiting time. So setting up the model is the quick part of it, but then running it and waiting for the results and getting to steady state conditions is the longer part of it. So the graph to the left was actually representation of the upstream elevation or inlet elevation that was assigned, and then the resulting flow rate that you get for that inlet elevation. So every time it makes that bit of a squiggle is when we ramped up the inlet level, and then it eventually reached steady state conditions when it flatlined effectively. But the interesting thing to kind of note is this is almost also representative of a calendar. So the first horizontal line is Monday, Tuesday, Wednesday, Thursday, and then Friday through to Sunday. And then again, we start at Monday, Tuesday, Wednesday, Thursday, Friday through to Sunday. So that's just a small nonsensical factoid for those of you who might be interested. Then eventually, yes, we do get to a stage discharge relationship for a unit width, which we then again just multiplied by the total spillway length to get to the purple curve that you see over there. The secondary y-axis to the right indicates the total flow for the entire spillway. Very interesting to note, the initial model setup that they did for the flood attenuation, they initially just used a C value for the normal OG relationship of 2.16. And if you fit a CD value with this simulated data, it basically equates to a CD value of 2.2. So the initial value of 2.16 that they used for the attenuation was actually very, very well estimated, which then luckily required little to almost no adjustment to that attenuation modeling portion of the works. So that's just a very interesting thing to note as well. And then because we basically still had the geometry available for the full spillway, and I personally did not want to let it go to waste, I thought we might as well just do a full-fledged CFD of the entire spillway section. So from the left, that was the survey image. We generated a solid. From the solid, we generated the void, which effectively is your solution space. And then from the solution space, we also generated a numerical mesh, which was a couple of million polyhedral cells. And then from that, we get to a complete simulation. We'll kind of see how the main curtain now almost starts to pull away from the nap as well, or from the OG, and then it gets to that fully developed curtain-like flow, which was also what was also good or beneficial from doing the full CFD was actually that we noted that this left lower bank is actually being overtopped. So it was a very valuable insight that we could also then share with the client. So apart from just giving them what the routing results through their dams were, we could also at least give them an indication of what would happen when they get full flow over their spillway, and also kind of see what happens to the downstream sections of the dam. So at NOC overflow level, it registered about 600 cubic meters per second, which coincided very well with the stage discharge relationship as well. So that was also very good. And that basically concludes my my presentation.
Thank you, Pierre. I really appreciate that. It was very exciting, quick and simple. I'll open up the floor for some questions. We don't really have anything in the chat right now. So if anyone has a question, please raise your hand so I can unmute you and you can pose your question to Pierre. I don't see any hands right now. I have a question for your upper dam, or this is the lower dam, right? And then you've got the upper dam, which was a bit smaller in
Yes.
depth. Was the p-value the one that you found on site, or did you select a low p-value because it looks quite small, the depth, I guess, of the spillway
Yeah,
is
so
what I'm referring to.
yeah, and typically what you would expect is that the p-value would kind of decrease due to siltation. But we did get the p-value from the upstream floor level from the as-builds that were available. We didn't make any adjustment due to siltation, as there was no way of knowing or understanding exactly what that depth would have been.
Yeah. And then did you experiment with some refining of the mesh in that deeper than the surface of the water? Because I found with my past experience of CFD a couple of years ago, that we kind of underestimated the effect that the three-dimensional flow has when the pool depth is quite small in relation to, maybe the lower dam, just to check if a finer mesh deeper than the surface actually had an effect. So it's just a question, an observation from what I experienced.
No, that's a very good question, and I just know Christian de Wet from the audience is burning to answer that one. But I'll give it a good bash of my own. But what I typically try and do is to run it up until steady state conditions, refine the mesh, and then run it a bit more to see if there's a real change in answers that you kind of get. And this mesh resolution actually provided fairly good answers. So there weren't major changes to the effective results.
Okay, so you did do like a semi-mesh independent study type thing.
Yes, yes, no, definitely.
Okay, cool. I see some questions in the chat now. Christian is asking, how long did the whole study take?
Thank you for the question, Christian. So we took about 2 weeks, not full time modeling, but model setup was probably in a day. And then running the model on the side, we were not really pressed for time, so that's one of the reasons why we actually didn't also do cluster computing for the simulations. But if you were to go for the cluster computing option, you would be able to get this done in a matter of hours. You could actually, submit all 9 scenarios or all 12 scenarios and let them run simultaneously on the cluster, and then in a couple of hours have your simulations completed. But because we were not really that pressed for time, we went for the local solution option. So just running it on a local in-house computer, and then just every morning checking on it, and then ramping up the flow depth.
Wow, that's actually quite quick. Okay, we have another question from Michael. He's saying, what was the C value for the upper dam?
Okay, so the upper dam, because you do have varying flow depths for your approach, and that relationship between your overflow depth and your P kind of is rapidly changing constantly. There's not a set C value. We did the calculations to determine what the C value is for each upstream depth to get to this theoretical versus a simulated graph. So it's not a single or a set CD value that you kind of have for that spillway. But we did do the comparison between the simulated values and the computed values, and they kind of did overlap fairly well. But you can refer to the design of small dams textbook to get the design calculations for the WES spillway.
Okay, we have one more question from Tala. He's asking, what was the roughness taken for the entire model?
Okay, so for the upper spillway, I just quickly go back to this section. We mainly simulated the portion that you kind of see over there. And because that's predominantly concrete works, we basically just use the absolute roughness of about 2 millimeters, which we assign to the concrete works. And then for the lower spillway, that's a bit different. So for the upstream face, let me just get to this image. For the upstream face of the spillway, as well as the downstream face, we again assigned a concrete absolute roughness value of about 2 millimeters. But because the floor is not concrete, it could be any value. We would not be sure. But the good thing at least is because your approach depth and resulting velocity would be very low, the effect of whatever your roughness selection on that face would be minimal, or nearly no impact on the overall hydraulics of the scheme. So whatever the roughness you assign to that bottom would not have a market effect on what's happening at the top overflow.
Okay, thank you. We also have Neil saying, Pierre, thanks for the presentation. Very interesting. What was the approximate cost of the study?
Wow, that's a tough one to answer. What we quoted, obviously we try and do cost estimates of our time. It's really actually a hard question to answer while trying to kind of give an indication of what your software licensing expenses would be, the time the person who does the modeling and simulation would be. So I'd say I can't really straightforward answer that question. I'm sorry, Neil, maybe we can have an offline chat about that if you're maybe interested in getting some CFD work done. But yeah, that's a tough one to answer.
I like your political answer to that question. All right, so I don't see any more questions. Christian is asking for a ballpark, saying more than 10,000 Rand or less than 100,000 Rand, somewhere there.
I'll give another political answer. It's between 10 and 100.
Okay, so we have Darian asking, has the risk of rock scouring been assessed downstream of the lower dam?
Okay, that unfortunately fell outside the scope of this study, but it would definitely be something that can be done with this CFD simulation software, which again I would more than gladly recommend you talk to Christian de Vet too. But yeah, that fell outside the scope of this study.
Okay, another question from Michael. What was the risk in assuming that C is equal to 2.18 for the downstream OG?
Oh, for the downstream OG, okay, the initial estimate was 2.16. It would effectively just underestimate your discharge for a given or set upstream depth. So depending on how you look at it in terms of attenuation calcs, you would be underestimating your peak outflow rate. But in terms of required volume to retain any flood water, you would actually be overestimating your pool depth inside your dam. So it depends on how you look at it, especially with attenuation type of calculations or modeling.
Here we have one from Andreas who is saying, what time step did you use for the simulation and what was the maximum velocity over the spillway?
Okay, so time step simulation, we typically observe the CFD, sorry, the Courant numbers and then try to keep those below 1 and adjust the time step accordingly. But if you now start to set up really fancy CFD simulations, you can actually have that time stepping be determined by the software itself. So you can actually set the software to monitor the courant numbers for you and accordingly adjust your time step, decreasing it if your courant numbers start to exceed 1 or 1.5, whatever the value you try to limit it at. In terms of velocities for the upper spillway, probably seems to be in the region of 7 meters per second. And then for the lower, that seems to be in the range of, at the free flow or the free fall at least, probably about 15 to 16 meters per second. But also to note that the free stream or the water surface profile at the free stream is probably not that important as your control actually sits at the crest of your dam. So having slightly higher courant numbers at that free stream surface would probably not be that big of an issue. But at the control itself, definitely you would want to maintain lower courant numbers.
Great, thank you. I'm sure that answers the question. Okay, is anyone going to answer a question again after I say there's nothing? Okay, there's no more hands and there's no more questions in the chat. So I'm going to close the Q&A session. Thank you so much, Pierre, for sharing your insights with us and for sharing your hard work and your model and for going into so much detail and creating such an entertaining session for Wednesday afternoon. Really appreciate the time and the effort that you put in. And we look forward to hearing from you and seeing your work in the future.
Thank you, Ashley, for the opportunity.
It's a pleasure.